Let's now move on to bases and dimensions. They are properties of vector spaces as well as subspaces. Let's start with a couple of definitions. The basis of a vector space or a vector subspace is the minimum set of vectors that will span the said vector space or the subspace. The operative word minimum there, what that implies is that the vectors in the basis set would be linearly independent. If you have a linearly dependent vector, that is kind of superfluous and there's no reason to have it there, and that will just increase the number of vectors without adding any value in the spanning ability of the set of the vectors. What it really means is that you need enough vectors to span the space or the subspace, but not too many. If you have one too many, that extra vector is going to be a linear combination and you don't want that. So it's a minimum set really. So let's take some examples. In our very first example, we had a red vector 1, 2 and a blue vector 3, 1. They were in R2 and I have two vectors here. Are they linearly independent? They are, and they will span all of R2. So you need two vectors in R2. You don't need any more than two. You need them to be linearly independent. Similarly, for R3 in example 7, we had three vectors, x1 and x2, almost the same as the ones in R2, except that I have an extra component there for the z part. But in x1 and x2, the z component is 0. But in order to compensate for that, I have a purple vector there with a z component. So together, these three vectors can span any vector in R3. The xy plane in R3 will be spanned by x1 and x2, and anything that is sticking out will just get a component along x3 also. We also had some examples where the vectors that we considered were not basis vectors. In example number 2, we had x1 and x2. As you can see, they were linear combinations of each other. What they would span would be a subspace along the line specified, either along x1 or x2. It's the same line. You don't need both those vectors to specify the line. You need only one of them. So too many vectors there. They're not linearly independent. So that is not a basis set. In example 3, if you think about the vector space of R2 and take these two vectors, x1 and x2, they're not enough to span all of R2. What they will span would be a subspace. Can you see what that subspace would be? It would be a plane of vectors, obviously, because there are two linearly independent vectors there. But what plane? It is an xy plane in R3. So it's a basis for a subspace in R3, but it's not a basis for R3 itself. You need three of them. Now, having defined basis set and basis vectors, we can define the dimensions of vector spaces and subspaces. The dimension of a vector space is the number of basis vectors needed to span the space. In the case of a vector subspace, it's the number of basis vectors needed to span that vector subspace. So that is it. Now, we put the basis vectors in a set and we called it basis set. And as you know, in the lingo of set theory, the number of elements in a set is called the cardinality of the set. So you can get a little fancy here and say that the dimension is the cardinality of any basis set. Dimension is a property, immutable property of the vector space or the subspace. It cannot change dimension. But the basis set itself, you can have many different basis sets. There are some basis sets that are preferred over the rest of them, but any one of them will do. So several linearly independent basis sets do exist, but all of them will have the same number of vectors within. That would be the cardinality, and that is indeed the dimension of the vector space or the subspace that we are talking about. So like I said, the dimension of a vector space or a vector subspace is an immutable property. For a vector space, dimension happens to be the same as the number of components. So in R3, all vectors will have three components and the dimension of R3 is just 3. That's why you call it R3. Rn will have a dimension of n. That means you will need n linearly independent vectors to span it, and any vector in Rn will have n components and elements of real numbers. Consider a vector subspace, a line through the zero vector in Rn. Its dimension is 1. If it is a plane going through the origin, then that plane as a subspace will have a dimension of 2. These things are all fairly intuitive. What it also means is that for a line of vectors as a subspace, you need only one vector to span that line, because one vector will specify a line. If it is a plane, if you have two vectors, that would specify a plane. Then there are these complicated space of functions, it's got infinite dimensions. We, being computer scientists, we don't really need to worry about infinities because a computer cannot hold infinities. So we will have very large numbers in modern computers, but not infinities. Now let's see how you would specify a vector space or a subspace. Vector spaces are easy. You would just say the dimension. So you just call a vector space Rn, R2, R3, etc. That's good enough. You don't have to specify anything else. In the case of a vector subspace, you will have to specify three things. One is the containing space. You have to say what this vector subspace is a subset of. So you can say something like S1 is a subset of Rn, for instance. Then you have to specify its dimension, because any number less than or equal to n could be the dimension of that subspace. You have to specify what it is. So if it is a plane of vectors going through the origin, then you have to say that the dimension of this subspace that you're talking about, dimension of S1, is 2. That's not enough. The third thing you have to specify are the basis vectors, because I need to know what plane it is that you're talking about. So from example number 6, we had these two vectors, and if you specify those two vectors as a basis set, I would like to see them as column vectors in a set. I would expect to see 2 in this case, because in item number 2, you told me that the dimension is 2. So this would be a complete answer, a complete specification of a vector subspace. I kind of mentioned in passing that if it is Rn, if you're specifying a vector space, you just have to say R something, Rn, R2, etc. It's because there is a preferred basis set there. That would be the columns of the identity matrix of that size. So identity matrix is an excellent basis matrix. Oh, by the way, a basis matrix is just a matrix in which you have the columns that are the basis vectors for the space or the subspace you're talking about. So take the basis vectors, instead of putting them in a set, put them in a matrix as columns, and that would be the basis matrix. Identity matrix is a very good one for all kinds of spaces. The reason is that the columns of the identity matrix are unit vectors, because it's 1, 0, 0, 0, 1, 0, etc. So they kind of specify directions like x, y, z in the coordinate space. Here's an example of I3 in R3. So these three vectors standing right here, they are very good basis vectors. And for that reason, in physics, you would call them I hat, j hat, and k hat. And any vector x, y, z can be expanded along I hat, j hat, and k hat, and can be expressed as a linear combination of these three vectors, as you can see very easily. Multiply the first one by x, so you get x here. The second one will get a y here, and the third one will get a z here. Add them up, you get the vector that you're trying to specify. More than being just unit vectors, they're also orthogonal to each other, because if you take the dot product, I dot j is 1 times 0, 0 times 1, 0 times 0, and they add up to 0. Any pair of these three vectors will give you a dot product of 0, indicating that they are perpendicular to each other, unless you're taking the dot product of a vector with itself, in which case you will get 1, indicating that they are actually normalized. Orthogonality defined for vectors is just that the dot product has to be 0. Now let's talk about orthogonality of subspaces, which is a slightly deeper concept. So for vectors, if the dot product is 0, that means x dot y, which is x transpose y or y transpose x as products, just gives you 0 as a number. Orthogonal subspaces basically means that if you have two subspaces, every vector in one subspace, if it is perpendicular to or orthogonal to every vector in the second subspace, then these two subspaces are orthogonal subspaces. You don't call subspaces perpendicular subspaces, you can call them only orthogonal subspaces. So one good example would be in R3, the subspace of the x-axis and that of y-axis will be orthogonal. Why? Because you take any vector along the x-axis and take its dot product with any vector along the y-axis, you're always going to get 0. Let's visualize that. Here you go. Vectors along x-axis would have the form x0, 0. This is in R3, so 3 components. Vectors along y-axis would have the form 0, y0. Obviously, you can see that they are perpendicular, so they are orthogonal too. But in order to verify, you just take the dot product. The dot product will be 0 times x plus y times 0 plus 0 times 0. So that adds up to 0. So the dot product is indeed 0. Another one would be the subspace of the xy plane and the z-axis. What it is saying is that any vector on the xy plane would be orthogonal to any vector on the z-axis. Let's see that in action. So I have my 3D space here. My xy plane, I have highlighted that in purple, and my z-axis, just a line of vectors, that is in blue of the type 00z. All the vectors in my xy plane, by the way, I have highlighted only the positive quadrant as usual because if I highlight the whole thing, it's kind of useless. So all vectors of the type x, y, 0, x and y being any number, would be on the xy plane. As you can see, if you take the dot product will turn out to be x times 0 plus y times 0 plus 0 times z. So 0, 0, 0, add them up, you get 0. So all vectors on the purple xy plane are indeed orthogonal to all vectors that lie along the z-axis, the blue vectors. Now let's actually think of a counterexample. The xy plane by itself is a subspace because all planes that go through the origin containing vectors would represent a subspace. So xy plane and yz plane are subspaces. So let's take a look at that and see something that is slightly counterintuitive. So my xy plane is in purple, my yz plane is in blue now. They look as though they are orthogonal, don't they? But they're not orthogonal subspaces. Let's see why. Well, if you just think about the obvious vectors, the one along the z-axis, 0, 0, z, and along the x-axis, x, 0, 0, they are indeed orthogonal. But those are not the only vectors in those two planes. You can consider some other vector, x, y, 0. It is in the xy plane because the z component is 0. And 0, y, z, that would be in the blue yz plane. Are they orthogonal to each other? It's kind of hard to see, but you can just take the dot product. That would be x times 0 plus y times y plus 0 times z. So that turns out to be y squared. That would be 0, only y is 0. But y doesn't have to be 0. The vectors may not be on the xz plane, it may be somewhere else. And those vectors are not orthogonal to each other. But even more simply put, you can see that there is an intersection of these two subspaces, and that's a line of vectors. Those are all vectors along the y-axis. So a vector such as this one here cannot be orthogonal to itself. That brings me to one of those edge cases. What's a single vector that can be orthogonal to itself? Remember, the property of being orthogonal, orthogonality property, is verified by taking the dot product of two vectors. So if a vector has to be orthogonal to itself, then the dot product of that vector with itself has to be 0. The only such vector is a 0 vector. So any other vector along the y-axis would not be orthogonal to itself, but that vector belongs to both the purple plane and the blue plane. So the orthogonality condition that all vectors on the purple plane be orthogonal to all vectors on the blue plane is not satisfied for the vectors that lie along the y-axis. So all vectors of the type 0, y, 0, where y is not 0, will not be orthogonal to itself, and that would violate the requirement for these two vector subspaces to be orthogonal to each other. Now let's talk about orthogonal complements. So we saw that two vector subspaces are orthogonal subspaces when every vector in one subspace is orthogonal to every vector in the other subspace. We tighten the requirement a little bit more, then we get orthogonal complements. If a subspace is to be the orthogonal complement of another subspace, then all vectors that are orthogonal to the subspace will have to be there in the orthogonal complement. So we use this symbol S perpendicular to indicate orthogonal complement of a subspace S, and this statement here that the orthogonal complement of S is the orthogonal complement if all vectors orthogonal to all vectors in S can be found only in the orthogonal complement. That statement may not be completely obvious to you, but we'll go through a couple of examples very soon. Mathematically, all it is saying is that the orthogonal complement is a set of vectors such that the dot product of that vector with any vector, every single vector in S is 0. One consequence of two subspaces being orthogonal complements of each other is that their dimensions will add up to the dimension of the containing space. That's because if there is something left over, there may be vectors in that leftover dimension that could be orthogonal to the space. But by definition, the orthogonal complement should contain all the vectors that are orthogonal to all the vectors that are there in the original space. Again, an example might make it easier. So here's one. If I have the xy plane as one space and the z-axis as the second space, subspaces, then these two subspaces are orthogonal complements of each other. Again, we can see that in our previous visualization. Here we go. My xy plane is highlighted on the positive side in purple, and my z-axis, which is another subspace, is highlighted in green. So all the vectors that belong to the z-axis as a subspace will have the form 0, 0, z, and all the vectors that belong to the purple subspace will have the form x, y, 0. Now, as you can see, regardless of what values you choose for x, y, or z, the dot product is 0. More than that, if you take a vector along z, can you find a vector that is orthogonal to it that is not in the xy plane? Can it be anywhere else? Remember, in linear algebra, all our vectors will start from the origin. So origin is a common point for all vectors. So with that extra information, you can see that there cannot be another vector in this 3D space that would be orthogonal to 0, 0, z. So xy plane as a subspace is the orthogonal complement of my z-axis as a subspace. That would imply that the orthogonal complement of the purple space is the z-axis. But let's ask that question once more. If I give you a vector x, y, 0, let's say 5, 3, 0, can you find a vector that is orthogonal to it? And could it be anywhere other than along the z-axis? You cannot. You are looking for, 5, 3, 0, and you want to take a dot product with it. And the only way you can make that 0 is by having 0 in the first component, 0 in the second component, and something along the third component because it's already 0 here. In other words, the only form that you can dot product my purple xy0 with, such that you get the scalar 0 as the dot product, would be 0, 0, z. So that has to be on the z-axis. So they are indeed orthogonal complements. Maybe a positive example is not enough. Let's look at a counter example also. Suppose you take S1 to be the x-axis and S2 to be the y-axis. Are they orthogonal complements? They are indeed orthogonal to each other, but they are not orthogonal complements because, for one thing, their dimensions don't add up to 3, containing space as specified here. Let's take a look at this one once more. So here's the situation. I have my vectors along the x-axis, x, 0, 0, and those along the y-axis as a second subspace, 0, y, 0. Take the dot product. The dot product indeed is 0. So they are orthogonal subspaces. But we can find vectors that are orthogonal to the x-axis that are not along the y-axis. For instance, a vector of the kind 0, 0, z is orthogonal to any vector on the x-axis, but it's not along the y-axis. Actually, any vector in the yz plane would be orthogonal to my x-axis, and any vector in the xz plane would be orthogonal to my vectors on the y-axis. So they are not orthogonal complements. But the easiest way of seeing it is by the fact that the dimensions don't add up to 3, because we're talking about R3. But indeed, if these two subspaces were in R2, the x-axis and y-axis, then they would actually be orthogonal complements, because all vectors that are orthogonal to the x-axis in R2 can be found only on the y-axis, nowhere else. So the statement is that my green subspace comprising the vectors on the x-axis is not the orthogonal complement of my red subspace comprising vectors that lie along the y-axis. Now, we saw that 0 vector is a special vector. It is the identity of addition, much like it is for real numbers, which is not surprising because real numbers is just a vector space. So it defines the additive inverse by saying that for any vector, we take the negative of the vector and add it to the original vector, you get 0. 0 as a vector. It is parallel and perpendicular to all other vectors. Why is it perpendicular to all other vectors? Because take any vector, dot product it with 0, you get 0. You get 0 as a scalar, So it is perpendicular or orthogonal to all other vectors. Any vector can be scaled by 0, a scalar number, to get the 0 vector. So it's parallel to all other vectors too. It lies literally on all other vectors. It's the origin. Now we know that in any n, 0 vector as a set would be a vector subspace because it's closed under scalar multiplication and addition. Scale 0 vector by anything, you get the 0 vector. Add 2 0 vectors, you get 0 vector. What's the basis of this subspace that contains only the 0 vector? What's the basis of this subspace that contains only the 0 vector? You might be tempted to think that it is actually a set that contains a 0 vector, but it's actually an empty set. In other words, you don't have to specify anything at all, which is a bit weird. The dimension of this subspace is actually 0. The cardinality of the basis set is 0. It's not 1, because if the cardinality was 1, that would mean that it's a line. But 0 as a subspace is just a point. And 0 is the smallest vector space. It is closed, it's got 0 dimension, etc. So mathematically, zeros are very interesting entities. It's been a counterintuitive thing, if you would allow me to share a little bit of history of mathematics with you. For a very long time, people did not conceive of this notion of nothingness among numbers, and that was first thought up of by an Indian. I think his name was Aryabhatta. That's when they realized that even though it was such an important number, people didn't even think of having 0 in their number system. Very weird. Now, just one pedantic point that I try to make all the time. We have what we call a coordinate space. That's where you have the axis x, y, z, or x1, x2, x3, xn, etc. So those are like a number line or a plane or graph paper, and the space that we live in. So you can think of the coordinate space as a set of points specified by the corresponding coordinates. And it also has the properties of vector spaces like closure under addition and scaling. So it is a vector space. More than that, it's got a one-to-one correspondence between this vector space. Every single point in a coordinate space as a vector space has a corresponding vector in the set of all possible vectors. So there's a one-to-one correspondence between them. But a vector space literally is actually just a set. You cannot visualize, you cannot imagine things inside. There are vectors there, and vectors are defined by the abstract properties of scaling being closed and the addition being closed and the existence of a couple of operations, and that's it. Any mathematical entity that obeys these properties can be called a vector, and there are many vectors that do not look like line segments with arrows in a coordinate space, as I mentioned in quantum mechanics and in Fourier transform and other transforms like Laplace transform and any kind of basis functions that they use to decompose functions into components. So they are abstract and bigger concepts than points and sets of points. So if you keep that in mind, you expand your domain of applicability when you think of algorithms later. And so keep this distinction in mind. It may not be a distinction with a lot of significance because there is a one-to-one correspondence. And more than that, they actually share the same symbols. R2, a vector space, and R2 is a plane also. So keep this in mind. When you think of vectors as line segments with arrows, you are thinking in terms of coordinate space, not in terms of the abstract vector space. And that might limit your imagination in certain applications. I'm just being a bit pedantic here. Even if you ignore this particular slide and think of vector spaces as coordinate spaces for this course, you will not get any kind of penalty anywhere because it will not come up, but it may later in life. So with this rather tedious intro, we are ready to actually look at linear equations again. Now, in terms of a different kind of geometry, not as shapes in some coordinate space, but as some kind of collections inside some vector space, abstract vector space. So that's where we will go in the next video.